Okay, so one operational definition, I'm not sure how that's supposed to look, and we're going to record this so that we can get this back to her.
Okay.
In my realm, we define variables, and this would be a category. We would call it a categorical variable. Either blondes have more fun or non-blondes have more fun, and we'd have two groups, and we would compare the relative sizes of the groups. Or how much fun they have. There has to be a way to quantify that, but I'm not sure what they're looking for on one. I just don't know, so I'm not going to even try to. That's not terminology we use in AP statistics. Number two, not real sure what he wants there, but in the realm of statistics, we are looking for evidence that either sends a hypothesis down in flames or evidence that a hypothesis is supported by statistics. So we collect a sample, we take some measurements, and if the differences are big enough to be more than just random chance alone, then we can say that we have significant evidence to support a hypothesis. But we never really prove a hypothesis. We have evidence for or against it. But I'm still not sure what really he's looking for there, because this is not the terminology that we use in AP statistics. Probably because AP statistics is general. It's a generic study that you can apply to all the sciences, and what you're doing is specific to the psychological sciences probably. And so I don't know those specific terms. I don't know that I can help you with one or two. But three, the median, you put them in order, you look for the middle one. So I think you've got that. Number four, Dr. Spock found a correlation coefficient of R equals 0.90 between IQ and social skills. So that means we had, on one axis, we had IQ, and we had to be able to quantify that, so we had actual IQ scores, because you can only get correlation coefficients with quantitative variables. And that's probably not the same terminology you use in your course either. And then you've got social skills on the other axis, and there has to be some quantitative way to measure that. If you have an R of negative 0.90, negative means the direction is negative. So as IQ scores get larger, social skills get smaller. So in general, you're looking at a picture where as you go from left to right, things are getting smaller. Negative 1, R of negative 1 would be a perfectly straight line. Every point would be on the same line, which means this has a pretty tight spread to it. I probably had stuff way too scattered here. But negative 0.9 means you have a strong negative association between IQ scores and social skills, which hopefully means that you can get decent predictions of one from the other. Okay, so interpret the correlation coefficient discussing strength. The strength is it's strong because R is 0.9. And there's not really a cutoff for what's considered strong or moderately strong or weak. But the closer you are to 1 or negative 1, the stronger. So 0.9 is pretty strong. Once you get down into like the 0.7s, I normally argue moderately strong. And once you get down below 70%, I'm normally heading toward the weak. And it's easier to tell if you have a picture, but definitely close to negative 1 is going to be strong. Direction is negative. And general conclusions that can be made. The only real conclusions you can make is that there is an association, a strong association between the two variables. It doesn't mean that one causes the other. You can't ever come to that conclusion unless you've done some experimentation that's properly designed. But you can argue that there is a strong negative relationship between IQ scores and social skills. Okay, so that's 4. Number 5. What are the advantages and disadvantages of using an experiment as a research method? The distinct advantage is that if you conduct an experiment, unlike any kind of observational study, in an experiment you can draw a cause-effect conclusion because you have the ability in an experiment to control sources of variation, to replicate to multiple subjects, to randomize your treatments, to use control groups, to use placebos. You can just control so much more variation. You can block for different variables that you think might have some sort of an impact on the results. So this is the biggie for an advantage. The disadvantage, I don't know, probably higher cost. It's harder to design. You have to be much more careful about how you design it. In an observational study, you go out and find a random sample of people and you ask them questions, you give them some, you measure something about them. So you can't draw as good a conclusion. You can't draw that cause-effect conclusion. All you can look for is an association or a change. But experiments are generally more difficult and more costly to run than observational studies because you have to control, you have to replicate, and if you don't properly randomize your treatments, then you're not going to get any useful results when you're done. There may be more to it in your class to discuss, but that's what I would say off the top of my head. Number 6. Comparing contrast descriptive statistics and inferential. So descriptive doesn't involve any decision making. So descriptive, you look at graphs, you analyze, you calculate statistics, you calculate means, standard deviations, and so you really just get to look at it and talk about it. So you can talk about where the center is, you can talk about how big the spread is, you can talk about one group being bigger than another group. In inferential is much more powerful because in inferential you do decision making. For us in AP statistics, that is either in the form of a confidence interval or hypothesis test. So you start with some sort of premise and you look for evidence that either supports that premise or gives you evidence against that premise and causes you to reject it. So the inferential is much more powerful because you are doing inference, you are drawing conclusions, and you have statistical evidence. You can draw statistically significant result. That's not the right words. You can talk about having statistically significant results because you can associate a probability with it, and you don't do that with descriptive statistics, because when you run a hypothesis test, you end up calculating the probability of having a change or a difference or a measurement that is so unusual that it could not have happened by random chance alone. And with descriptive, you don't have that kind of power of decision making. Alright, moving on. Hope this is helpful. Number 7, what is an outlier? Detail 2 statistical tools where you would especially want to pay attention to the presence of outliers. Okay, so an outlier in general is a point or a value that doesn't fit in with the rest of the data set. In one-dimensional world, there's actually a rule for that. If you have a set of numbers like 3, 5, 8, 10, 12, 20, an outlier is explicitly defined as any value beyond 1.5 interquartile ranges from either quartile 1 or quartile 3. So let's see, of course I had to make up an even number because that's not easier. Let me add the 1 here. So we have an odd number of data numbers. The middle one's 8, so here's your median, which is your Q2. And then the bottom half of the data is here. The middle of it is 3, so 3 is Q1, your first quartile. The top half of the data is these 3. The middle of that is Q3, that's 12. Okay, the difference between Q3 and Q1 is called the interquartile range. The difference between 12 and 3 is 9. So the distance between those quartiles, if you made a box and whisker plot, it would be the width of your box. Okay, if you multiply that by 1.5, that's 13.5. So any value that's more than 13.5 below Q1, so we call that the lower fence. The lower fence is the Q1 minus this 13.5, which is technically negative 10.5. Anything lower than negative 10.5 is an outlier, so you don't have an outlier on the lower end. The upper fence is 13.5 more than Q3. So Q3 is 12, you add 13.5, and that's 25.5. So anything bigger than 25.5 is going to be an outlier. That's your upper boundary. You don't have anything bigger than 25.5. So you don't have an outlier in that data set. In two-dimensional world, which you may have to look at, in two-dimensional world, you're looking for a data value that doesn't fit the overall pattern. So if you have a pattern of points, say something with a negative association like this cloud of points, and you have another point over here, that point does not fit in with the overall look, and that outlier is troublesome because he influences your line of best fit. Without the outlier, your line of best fit would go here. With the outlier, it very well could do something kind of like that. It could be an entirely different model. So outliers are really important because they can influence your model so that it doesn't give the right picture of what's really going on with your data anymore. And I don't know if I totally answered that question, but this is your biggest problem with outliers, is that it gives you a wrong overall look at what's going on with your data. Similar thing would happen in one dimension. Let's say these are how much people get paid per hour, and you've got some fella up here that gets paid $300 an hour, and you add him to the data set. He's definitely an outlier. And if you add him to the data set and you average your hourly pay, it's going to influence your average toward the upper end. It's going to make your average look a lot bigger than it really should look. So outliers in the one-dimensional world make your means and even your measures of spread, like standard deviation, appear much bigger. And if you only look at the mean and you don't look at the set of data, then it can give you a wrong impression about what your data looks like. So it really influences those measures of center and spread. Okay. What we got next? Number 8. List 3 commonly used measures of central tendency. Means and medians and modes are the 3 typicals. Modes we don't find particularly helpful in AP statistics. Modes we don't really think of as numbers. We think of those as where the most piles up, and that's kind of where on a graph of a curve, it's going to be where your hump is, where your high point is. 2 commonly used variability. Probably the most useful ones are, or the most commonly used ones, and I'm off my screen here. For part B, the standard deviation is the one that usually accompanies means. So standard deviation gives you pseudo-average distance of all your data points from the mean. And then the interquartile range is one that we often use with one-dimensional data when we want to know how that middle 50% behaves. Okay. Number 9, type 1 and type 2 errors. Okay, there's a great adventure. Okay, so errors. Type 1 versus type 2. Okay, so in the realm of statistical testing, I like the box, and my class hasn't gotten to the box yet, so this is stuff that we haven't actually gotten to in AP statistics yet this year. But you have 2 things going on in the realm of statistical testing. You have your hypothesis, what you hypothesize in your null hypothesis. So you either hypothesize that you make a hypothesis, and either that hypothesis is true or that hypothesis is false. Now, you don't really know the truth, otherwise you wouldn't be running a hypothesis test. So you're running a hypothesis test because you don't know the truth about the population. You're looking for the truth, and you're going to use statistical evidence from a sample to get at the truth. So the hypothesis is either true or false. You're looking for the truth. One of these 2 things has to happen. You're just not sure which one it is. So you run your test, you collect some statistical evidence, you run the test, 1 or 2 things could happen. You have a decision, okay? Your decision could be that you reject your null hypothesis. So you have evidence that is so strongly in favor of your alternative, it doesn't support your null, and it so doesn't support your null being true that you have to believe it's not true anymore. You could fail to reject, and I know I'm lefty and that doesn't work very well here. You could fail to reject your null. So this is if your p-value is higher than 5% normally, if 5% is your alpha level. We normally use 5% for our alpha level in AP, but that could be different depending on your circumstances. So if your alpha level's below, if your p-value is below your alpha level, you'd reject. If your p-value is bigger than your alpha level, you would fail to reject. If your null is true and you reject it, you made a bad decision. So that's wrong. So that's a frowny face in my class. If it's true, we shouldn't have rejected it. But it happens. So if you think about how court cases work, this would be a case where your defendant would be innocent, but we send him to jail. He's innocent, but we reject that premise that he's innocent and we convict him. That's an error, and that's called a type 1 error. Type 1 is when your null is true and you reject it. So you start with truth. Truth is the important one. So you start with truth. Hypothesis is true. That's type 1. That's kind of how I keep up with it. If your hypothesis is true and you don't reject it, that's a correct decision. This is good. That's what you want to have happen. So this is when your dude is innocent and you don't send him to jail. That's a correct decision. We want that to happen. If your null hypothesis is false and you reject it, that's good. That's what you want to have happen. That's a good decision. In the realm of statistics, we usually say that this is where the power of the test lies. The whole purpose of taking a fellow to court is because even though we presume he's innocent, we really think he's guilty, because we have to have some evidence or we couldn't even take him into custody to start with. So we say he's innocent, we presume he's innocent, but we really think he's not. So that's a false null hypothesis. If we reject it, that means we're going to reject the notion that he's innocent. If he's really guilty, that's a good thing. And the power of the test is basically the power to reject a false null hypothesis, which in the judicial world is the power to send somebody who's actually committed the crime to jail. That's what we want to have happen. This is what we really want in the long run. And then this last box here, if we have a false null, but we fail to reject the null, which means we don't think it's false, that's a bad decision. That's wrong. And that's a type 2 error. Okay? So type 1 is when the null is true, we reject it. Type 2 is when the null is false and we fail to reject it. The easiest way to think about these, I think, is to think in terms of that criminal justice system. He's innocent, we convict. That's bad. He's guilty, we set him free. That's bad. Which one is worse? Kind of depends on your ethics. In the realm of medical testing, the null hypothesis is that the new medicine is just as good as the old medicine. Okay, if we reject that, then we have committed an error. In this case, the new medicine wasn't really better, but we said it was. And we're going to produce and manufacture and treat people with a medicine that's not better. That's not a terrible thing to happen, but this other one's bad. If the new medicine really is better, then we'd have a false null. We fail to reject it, it means we don't think it's better, so we don't market it. So we have a cure for cancer, but we don't market it because we don't think it actually works. So in the medical field, sometimes we think the type 2 error is worse. In the judicial system, we think type 1 is worse because we think that sending an innocent person to jail is worse than setting a guilty person free. So which one is worse kind of depends on the scenario that you have going on. 10. Compare and contrast the null hypothesis and the alternative. The null is your sort of status quo. This is where you say there's nothing interesting is going on. Nothing's going on. So blondes don't really have more fun. The new medicine's not really better. Our blood pressure isn't going to go down with the new medication. The guy's innocent. So there's nothing interesting going on always. The alternative is always the antithesis of that. So there is something going on. So something's going on. So this is we're looking for evidence that he really is guilty of the crime, or that new medicine really is better, or blondes really do have more fun. A lot of times you take your null and put a not in it, you have your alternative. So they should be in opposition to each other. And you're running your test on the null, and at the end of the day, if you reject it, then you believe that the alternative is true. Another question it was back there somewhere. Oh, no, it was the next page, isn't it? That Kendall's sitting here flipping pages for me. Go on to that next one.
This one?
Yeah. The one-tailed and two-tailed test. Okay, so the one-tailed, two-tailed is really about your alternative. If your alternative hypothesis is that if we say that something is greater than or less than something else, so we're looking for one direction or the other. So blondes have more fun, blondes have less fun. The blood pressure went up, the blood pressure went down. If you're only looking at one direction, that's a one-tailed test. And so when you think about the picture of that, normally what you have is you have some null hypothesis parameter that you've started with. And you want to know whether your sample lands somewhere far enough above, if you've got a greater than, far enough above that you're out here where there's not a whole lot going on in that tail, then you reject your null. If you have a two-sided or two-tailed hypothesis, you're really concerned about a not equal to, which is this is a one or the other. This is it could go either way. So this is a situation where blondes don't have the same amount of fun. They could have more fun or less fun, but they don't have the same amount of fun. And in that case, your null parameter is here. And if you get a value up here, you'll reject. And if you get a value down here, you'll reject, which means you actually have to double your probability of it happening. So it's really about how your alternative is phrased. If your alternative is about a greater than or a less than, more than, less than, at least, at most, then it's one-tailed. If it's is different, normally you see that the key word here is that something is different. Different means it could be lower or higher. So you could go either way. All right, keep on going. Compare and contrast the z-test and the t-test. Now, I don't know how the college professors look at this, but in our world, we use a z-test for categorical data. And I think probably your terminology is going to be different. You might call it nominal data. I don't know if that's the same term you'd see or not, but we'll take a stab at it. So this is when you're talking about hair color, eye color, gender, whether you're going to vote yes or no to a constitutional amendment.
So something that puts them in a group together.
Yes. So this is something that if you graphed the data, it would be like a circle graph or a bar graph. So you have categories, and you just count how much is in each category or the percentage in each category. A t-test you would run on quantitative data. Again, that may not be what I'm off the picture. I think actually it might have been at my tools in the way there. I think so. T-test is quantitative data. You may call that something different. I don't know what you'll call it in your class. It may be something different, but this is anything with units. So if you're measuring change in blood pressure, if you're comparing weights, if you're trying to find out that men tend to be older when they get married than women, anything that compares things with units, age, weight, number of people, I don't know. Units is really the key word. If it's measured in inches or meters or pounds per square inch or anything like that, then you're in quantitative data world. So weights, heights, pounds per square inch. I don't know, just think that's a physics thing. Your blood pressure, so your HDL, cholesterol, those sorts of things. Things you would graph on a number line, you're going to use a t-test on. Now, some old-fashioned professors use z-tests on quantitative data if you have certain conditions that are met. But that was. I'm going to be frank. The only people that still do that are the ones that haven't discovered modern calculators. If you have a modern calculator, you would never run a z-test on quantitative data because t distributions have more variability than z, and quantitative data has more variability than categorical. Because categorical is about percentages, and quantitative is about means. And the problem with quantitative is you never really truly know your population standard deviation, and so you have to estimate it here, and the t-test allows for the estimate you have to do for your standard deviation. And I hope that's helpful. But this is the key. When I teach hypothesis testing at the end of the year, and we've learned 9 different hypothesis tests, and my kids have to decide which one to use when, this is the defining difference. Do you have categories or do you have units? And that determines which test you use. Overview the appropriate use of the chi-square. Okay, I need a new page. You can take these pages with you. I don't know if it'll be helpful or not, but we'll try. So chi-square test. Chi-squared is, and again, my big left hand's in the way, chi-squared is used for categorical data with more, oh my goodness, I can't go fast enough, more than 2 categories. So let's say that you wanted to compare, one of my favorite ones is we always play with M&Ms. So if we have red M&Ms and green M&Ms and blue M&Ms and brown M&Ms and yellow M&Ms and orange M&Ms, and the M&M's Mars company says that there's a particular ratio that exists for each of those colors, and we get a bag of randomly packaged M&Ms and we want to test whether or not they're telling the truth, and we count them and we compare, you would use a chi-square test, because a chi-square test allows you to test multiple categories. And what you'll do in a chi-squared is you'll take what's in your bag, what's in your sample, compare it to the quantities that M&M Mars says you should have of each one, and you're trying to quantify how big the differences are. And if the differences get too big, then you decide that you don't believe in M&M Mars, that they're lying to you, that that's not really what they're putting in the bags. And you get a large chi-square value, and then you can reject the null. There's actually 3 different chi-square tests. This one's a goodness of fit test. That looks like the only one you have to do. We do 3 different tests in AP Statistics, but this is the goodness of fit test and how it would work. It would also work like if you had a group of people and you were trying to decide how many of them were lieutenants in the Army and how many generals and corporals, and you might take the percentage of all those ranks for the general population in the armed forces, and you might compare that to the women and their ranks. And if those are different enough, then you would reject the fact that women are treated the same as everybody else, and you might have an argument that women don't have the same ranks as the general population does. Okay, moving on. 14, why is an understanding of research design and statistics a necessary component of psychology curriculum? I'm going to leave that one to you. 15, if Jack scored a 15, oh, we actually get to do some statistics. Hallelujah. If Jack scored 15 on a test, okay, so his score was a 15. So his actual X value was a 15. And the population mean of 20. So the population mean, that's mu, is 20. Now, I don't know if your professor uses Greek letters or not. We're all about Greek letters for parameters. But I understand that some college people use a capital M there, which I find downright offensive, but I can't help that. And a population standard deviation of 5, so we would use the Greek sigma here. I'm not sure what your professor would use. He may go with an S. I don't like it, but I don't have to like it. It is just what it is. So the population standard deviation is 5. What is a z-score? Okay, so the formula for a z-score is I like the wordy one. It's the observed quantity minus the mean over the standard deviation. Okay, so you just need that formula. So your observed amount is 15, your mean is 20, your standard deviation is 5. So that's negative 5 over 5, which is negative 1. Which means this person, Jack, has a score that's 1 standard deviation below the mean, which is not terribly unusual. What does the z-score you computed mean? It means that Jack scored 1 standard deviation below the mean. That's really all you can say about it. You can't really calculate any probabilities or talk about normal distributions or percentile rank because you don't know that the test scores, you don't know that the test scores were normally distributed. They didn't tell you that, so you don't want to take it any farther than just to say it's 1 standard deviation below the mean. Okay, 16. Who would win an arm wrestling contest between Donald Trump and Bill? Really? Okay, I'm going to leave that one for you because I'm not even going to tackle that. Okay, so that gets that. I'm going to stop that one and see what was in that old email. So that one's 30 minutes.